Josh from the Kilted Filker Workshop here with my handy dandy chisel pointer to go over a walkthrough in detail of my scale model Roman Palintone Ballista. This is an actual period correct, or as period correct as we can be, torsion ballista, meaning it was meant to fire rocks or boulders or large objects at buildings, as opposed to the Scorpio over there, which is intended to fire bolts or arrows at people or smaller objects. As I said, this is period right based upon the works of Vitruvius, with a little bit of engineering archaeology on my part on how to make this happen. One of the problems that reconstructionists have is that there is no one complete set of works from antiquity that describe how these work in detail. Some of it, in the case of Vitruvius, the measurements were actually corrupted over time, and you can't build the way that his writings describe it. Other works of Philon and Heron are partially missing. We have found some extant pieces of Scorpios, but we have not found any pieces of Palintones. But we have plenty of descriptions of them, we have plenty of references, and as well as plenty of contemporary pieces, or plenty of contemporary pieces of art or sculpture that describe them. So from a design point of view, this was my own design. It was, again, based upon the works of Vitruvius, as well as what some modern reconstructionists have done. I've taken sort of the best of them, as well as what some members of the Society for Creative Anachronism have done with some of their builds and some of the lessons that they've learned. The pieces of this are very simple. First, you have a base. The base is very simple. There is some, I don't want to say arguments, but people have thought that the base itself was split into two parts. Some other scholars have thought that that was a mistake by an early scholar named Schramm, who lived about 100 years ago, where it talks about having a connection up top. Most likely this was one piece. The yoke here is fixed. It does not spin left to right, although I made this model able to spin up and down. That was for demonstration purposes. Reality is that these engines were so massive when they were built is that they were in one position. And the way that you would change the power is by how far back you slid that, and we'll talk about that in a minute. So at the back of the ballista is what's called the stock. This comes in two parts. You've got the table back here, which is just literally his job is to keep the ladder, which is this part, at a certain position relative to the headstock, which we'll talk about in a minute. While this is structural in the sense that it lifts it up, it does not move. And in fact, I've got the ladder and the table are glued together. The historical docs do not talk about how they were connected. Some people have used nails and screws, others have just glued. In the ladder is what's called a slider. That is this piece here. It literally, its job is to slide back and forth, right? As you rotate the windlass, which is this piece at the end, the slider moves back and forth. The reason why this one is having a little bit of trouble sliding is because it's been a couple of months since I've last used it, and it's probably bound up a little bit. So, attached to the slider is the trigger. The trigger here is a Roman period right trigger. It's got one finger. That finger is meant to catch the back of a bow strap. In this case, I have a string. That was just so I could test the operation of this. In reality, you would have a thick strap with a basket in the back where you could hold a rock. And the way that these triggers work are very simple, and they've worked for 2,000 years. You simply then take the end of this, you clasp it in the trigger, push this down, and then stick your trigger piece in place. Now, this centerpiece cannot move, and it can take a very high force. And then simply the way that you fire it is just to pull this back, and then the force of the rope or the bowstring against the finger lifts that up and it releases. This part of the slider itself, the wooden part, is non-structural. All of the force is within the trigger itself. In this variant, and there were many variants, I have the rope going to both sides of the trigger with, as you can see here, in the windlass, so you can pull it backwards as well as pull it forwards. And there's a safety device here called a ratchet, so that while you're pulling it back, this won't fly forward. It helps if you lift that up. So I can now move this forward and I can move it back. So at the front is the headstock, also called the torsion frame. That is this part here. It is also connected by a pair of arms. These arms serve two purposes. The first is that it positions this relative to this and just gives you an extra point of connection. And it also transforms. It also moves the load from the front here to the back and prevents any sort of twisting or torquing where the headstock is connected to the torsion frame. So the torsion frame itself, and let me stand up as I talk about this. The torsion frame itself consists of what are called two half springs that are then connected via these cross members. So you could take these cross members apart, although in this model it's glued. You would then have two pieces that come out. Each of these have got two stanchions, an inner stanchion and an outer stanchion. The outer stanchion is notched in the back and then extended in the front. That gives you additional room for the arms to swing. The swing arms are designed to strike the center stanchion here, as opposed to the euthetone, where in many cases they don't. At the top and the bottom are what's called hole carriers. You've got a top hole carrier and a bottom hole carrier in each half spring. And then each hole carrier is plated in metal. In period, it would have been a ferrous material. Then you have a washer and a lever. The job of the washer is similar to a washer today, where it's just a spacer. Many of them in period, especially the early ones, were made out of metal, but the later ones, especially the Vitruvian designs for the larger Palintones, were actually made out of wood. And there's a reason for that. Even though wood is not as strong, one of the things that you might notice about this hole here is that it's oblong, right? It is wider than it is shorter. And the reason for that is this lever here, right? And the lever was intended to be a place where you could then take a wrench and turn this to tighten your ropes. But because of the presence of the lever, you're taking away anywhere from 10 to 20% of the space for rope. And because these are powered by rope means less force, right? Which means less distance or accuracy depending on your goal. So Vitruvius came up with the design of having an oblong and then having it chamfer into a circle at bottom. Kind of hard to do if you're casting this out of bronze or another material, but very easy to make out of wood. Again, we haven't found any wood washers, but there are descriptions of them in period. And the reason why there aren't any wood is that, well, most of them have rotted. So the way that you torsion the rope, and in this case, the rope in period would have been made out of human hair or horse hair or sinew or even hemp. The Romans were very innovative. They would have used whatever they can do. Some of the modern scholars say that the rope should be 1/6 the whole diameter. Other scholars say 1/16. What you see here is approximately 1/16. I found through testing that was much better, much more reliable. Now, for those of you who are experts in ballistas, you will notice this isn't very tight and the rope work isn't all that good. To be blunt, I had depowered both of these models when giving some demos because of people who were coming up and touching them. And if I wasn't watching them every minute of every demo, something bad could happen as people would think it's a toy, which is why the ropes do not look all that great. And the reason for the zip ties were just to help me keep each of the strands, just so I could keep them from tangling up. Now also what the Romans did, or the Greeks before them, is they would have had the ropes dipped in oil. Part of that is that now it allows the ropes to slip easier. And one of the things that I did in a full-scale version was I used boiled linseed oil. That also made the ropes a little plier, or it made it a little springier, excuse me. And as I used it, the ropes actually evened out, which resulted in a loss of power. Now I just need to, tighten it down some more. And what the Romans did is they had holes. Right now in this specific design, this is bigger. That's just because that's how I came up with it. There's many different variants of washers out there. This one isn't exactly period right. The one I made full scale is, and I'll show a video on that one at some point in the future. As far as plating, this one has got plating around the stanchions. This plating was structural in the sense of it helped keep the stanchions together. It was not necessarily defensive, although likely there would have been additional plating around it to protect it from attack. This was really structural, right? So anyway, the arms here in period would have been 7 times the hole diameter, and they would have been straight. What they also did is they made it out of laminated wood. So this is just a 2-piece thing. I made it on a CNC. You can see where I had alignment pins. But if I were, when I made this full scale, I used 1/4-inch laminated wood. Because in this Palintone design, the middle stanchion is offset from the outer stanchion, you now have got room for a much bigger arc of each arm. If I pull the arm back, and let's see if I can do this with one hand. We'll pull it back. Anyway, so that's why this is offset a little bit. Of my small scale Roman Palintone walkthrough. One thing about Roman engineering that I don't remember if I talked about in the first video is that every dimension, everything in this model is based upon the size of the hole right here. And I built this to a 1-inch hole, which made all of my calculations easier, right? So if this were then a 1/4-inch for a 1-inch hole, if I went to a 4-inch hole, this would then be 4 times 1/4 or 1 inch thick. Makes it a lot easier. Also makes it, very standard. So if you look at the Vitruvius over here, this one also has a 1-inch hole, but is much smaller. That's because of different parts. This one likely would have been built anywhere from 4x to even 10, or I saw some tables showing 20. Some of these were huge. There were also many different variants. To talk about the windlass here, the smaller windlasses would have only had one rope to pull it back because they were small enough that you could just push it forward and then catch the rope. I've seen drawings where they had multiple windlasses. I made this one so it's got a rope on either end. And if we walk around front, I've got a bearing where the rope connects, or not connects, but rides, and then comes in on the back end. So the way that this would have worked operationally. So it's in a position now of I have just fired, right? The trigger is back, the slider is back, and the latch is down. So the first step is you want to push the latch up. That releases this mechanism here. This is a safety mechanism because as you're pulling this back, there is nothing to prevent this from flying forward. So again, this is a safety mech. Other variants of this had one on either side. In fact, the one that I made that's full scale has got one on either side, again, for redundancy. So the first thing that you would do is then spin this up until you are able to catch the rope. Now, this one has got a string. In period, it would have been an actual strap. And then the strap itself would have had a bucket or a basket that you would then put the rock or payload in. But so what you would do is you push this up, you take the end of your rope, put it in, slide that down, slide this in place. Now you are locked, right? This cannot come up because this keeps it in place. This simple 2,000-year-old design is able to withstand very high loads. This is fully functional. So what we're going to do is the next step is once you are locked in place, you put your ratchet back down, again, for safety. What the Romans had, they called these hand spikes. And all that you would do is simply put them in the hole and rotate, right? Pull it out and rotate. Now imagine you're having people on both sides, but because this is not torqued down, this is at a very light setting, I am able to just pull this back by hand. And I broke my axle. Oh, this is going to make for a great video. So let's see if I'm able to continue pulling this back, and then apparently I have some repairs to make. So you keep pulling this back. Now, one of the things about the ballistas, and sorry, I'm laughing at this. This is rather funny. That here I am recording a video and I broke the model. Is that you can fire from any position along this path. I do not have to pull this back all the way. If I wanted to take a lower powered shot, I could fire from here or even fire from up here, right? So once you are in the position that you want to fire, you simply take whatever it is you want to launch. And I'm going to use just this wooden dowel. It's technically the handspike for the Vitruvius, but it works. So I'm going to place it along the string. You want it to hit the string or be touching the string, and then maybe give yourself a countdown. 3, 2, 1, fire. And the stick landed. You see that black mat all the way over there? That's where it landed. So at this point, the firing cycle is done, and you would repeat it, assuming you didn't break your cheap ass axle. So mental note, when I rebuild this, use something stronger. There you have it. Thank you for enjoying my video. Josh still here with his handy dandy chisel pointer for part 3 of our video on firing my model Ballista, and I'm still can't believe I broke the windlass. And here's exactly what happened. Because I haven't played with this one in a while, I left the lever down, and then I turned this forward and it snapped the wood here. So mental note: 1, don't do that. 2, don't do that. And 3, I'll rebuild this with something stronger, maybe even metal. But you get the point. At the end of that video, after I broke this, I shot a stick, this here stick, in my side yard here. I just measured it. It is about 60 feet or about 20 yards. Now, what's notable about that is this is a blunted piece relative to the size of this. However, I am able to take my hand and pull this arm, here, let me do it from a seated position, back pretty far, pretty easily, right? Same on the other side. I should not be able to do that. And the reason why I'm able to do that is because I detensioned these ropes a while ago when I was using this as a display piece because, well, stupid people will come up and be stupid, and it was a matter of safety. But even with this under pretty low power, I was still able to launch this 20 yards, right? So you can imagine what I could do with this at full power. One of the amazing things about Roman technology, and here I'll use my handy dandy pointer, is that these things scaled linearly, which normally does not happen, right? If you build one of these to the right specs and you fire a bolt or a rock of the right weight for that right specs, it will go a certain distance. In period, they've said even up to 300 yards, especially for the bolt throwers. But the really cool thing is that if I take a rock and I then go much bigger, they have a formula where you can take the weight of that rock and it will then tell you the size of the hole that you need. And as long as you follow that and you literally scale up this, you will be able to throw that much heavier rock the same distance. Now, if you want to get a further distance, right, you could put in a smaller rock relative, but then you might have other effects like aerodynamics or whatever it be. But that's not what I really wanted to talk about in this video. This video, I want to talk about the ropes. And also, I can't believe I did that. So people who are watching this, you know what? No one's perfect. But here we go. So in period, if you read a lot of the documentation and if you read what a lot of the scholars tell you, what they tell you is that they had people with a musical background wind the ropes. They would wind it up and tighten it so tight that if you plucked it, it would resonate at a certain note. And that's how you knew that it was tight. There's only one problem with that. And that is now all of the rope and your force vectors are vertical. So if I either turn my washers or I pull the arm back, all of the force serves to just compress my torsion frame. So one of the things that in talking to one of the siege masters in the SCA, and for those who don't know, that's the Society for Creative Anachronism, had explained that, and we don't know if this came from the Greeks who actually lied to the Romans about winding the ropes, but there are period documents that show ropes that are wound like this. And what he had said is take the measurement from here to here, basically your torsion frame minus the washers, multiply that by 1.3 or an additional 30%, and then the distance from here to here and here to here. Make your rope skeins off of your ballista, then load it up and then twist it down. There's two advantages to that. The first is that it would take you all week if you had to load a full-size production thing where every strand was tight because you got to load it in and pull it through every time, versus if I load it on a table, right, I can do it in a matter of an hour or so. The second one is now the force vectors that I just talked about, instead of being straight up, and you could see it here, they're now at an angle. And when fully tightened, it'll actually get down to about a 45-degree angle. Now, the force of the rope is acting on the arm itself and not just to compress the torsion frame. So I was actually able... Yeah. So the astute followers of this video might have noticed we somehow magically transported from outside in daylight to inside at nighttime. That's because this kilted filker broke one of the key rules of sieging. The first of which being, don't marry a girl from New Jersey. But the second, and even more important, is always make sure your phone is charged, because my phone died right in the middle of my sticking. So, we were talking about the ropes and the force vectors and how I accidentally proved that theory out. When I was assembling this model, first thing I did was built the actual torsion frame, and then I was working out the arms. Well, one of the things that you'll notice about these arms are the only thing that keeps these arms attached are the ropes. So what I was doing temporarily was I just took 10 loops of the same rope and I tied it tightly the way that some of the documentation has you do it. That way it could keep the arm in place while I could test the geometry of the string and some other pieces. And then I decided to tighten it up a little bit just so I could get in just a couple of shots because I wanted to see how this thing worked. And what I noticed was I could only turn each of the washers maybe a quarter turn. So then what I did is I took one of the ropes out and I did it this way, where I made 10 loops, but I made it 30% bigger based upon this dimension. And so I was able to keep tightening that down significantly more than I was able to tighten this one down. And I noticed a dramatic difference in how the two different arms operated based upon how I wound the rope, even with the same amount of rope and trying to get what I thought was even tension. So anyway, this is one way to wind the ropes, and part of the reason why I'm talking about this is when I was doing my siege work and my initial research and investigation, I could find very little on the ropes. I'd found some Reddit threads, I'd found other posts, people talking about you have to use triple twist rope, not braided. But I tested both triple twist and a solid braid, meaning not rope that has a solid core and then a braid on the outside. These were ones that were braided all the way through. And I had found that the braided actually seemed to work better than the triple twist, which was a little counterintuitive. I thought the triple twist would work better. Also, one thing to note is that by having more rope in here, you actually are able to get more power. Think about it. If you took the same amount of rope and have it straight in this 1-inch hole going all the way up and down, and then on the other side, I take that additional 30% and I twist it, right? The more that you twist it, it will shrink and it will fill up this hole. You've effectively got more rope in here that can take, again, additional strain. And that could also be a part of it, not only the force vectors, but there's actually more rope in the skein than on the one where it's straight. So if you are making your own ballista, I would certainly do some experimentation. I would try it out. On the Euthetone over here, I actually experimented with different size rope. I experimented with hemp. I experimented with cotton, all sorts of different materials. At the end, nylon works. It's what almost every recreationist does. Recreator, anyway. And there's no need to go with a sinew. One of the things about hemp is it absorbs water. And so these models for me were test beds, so I could build the full-scale one for SCA Combat in an event called Penzik, which can get very wet and humid. And if those ropes start to absorb that water, who knows what can happen. And the nylon rope seems to work for me pretty well. So anyway, there you go. I will post details about this build and the build for my Euthetone in the links. I will also post links to the Society for Creative Anachronism and some of our Siege Combat in the links as well. Please feel free to look us up. Please feel free to email me if you have any questions. And I'll be posting future videos about the Euthetone. I'll be comparing the Palintone to the Euthetone. I will also be showing videos of my full-scale ballista that is made for a 4X, meaning it's 4 times as big as this. I reinforced it in places and I made it SCA compliant. This one we actually used in combat, but there'll be videos about that, how I built it, why I did what I did, why I didn't do what I didn't do. Also, the plans for both of these. This one, I literally had plans on pen and paper and then built this by hand. This one, I put the plans in Fusion 360 and made the parts on a CNC. I will eventually be publishing this as well as what I use for the full size. So if anyone has got Fusion 360, you can then literally build exactly what I have here. Anyway, thank you very much.